show that t squared is equal to 4 pi squared multiplied by r cubed all divided by gm, where all terms have their usual meaning. So this is actually the expression for the period of rotation that a planetary body would actually make around another planetary body. And we are actually required to derive this. We need to show that this expression is actually correct. Now, let us say that you have the sun, and this is represented by this diagram, and you have another body. In this case, we're going to say this is the Earth, and the Earth is orbiting the sun. So there is actually going to be an orbit that the Earth is going to make. So I'm going to represent this with a circle. Hopefully I'm going to have a perfect circle. Yeah. So we know that there is actually going to be a radius between this body and this body. So here we have this as the sun, and this is going to be the Earth. Now, if you have a line or, well, let me just say that is a distance from the middle of the sun to the middle of the Earth, that will be the radius for the rotation of this Earth. Now, maybe this Earth is moving in this direction, whichever direction at all, but we just know that the Earth must move around the sun. Now, from the Newton's universal law of gravitation, we have that the force, I'm just going to call that as F grav, that is the force of universal gravitation. You can express it as G multiplied, that is a G multiplied by M multiplied by small m, and this will be divided by r squared, where the capital M or the uppercase M is actually the mass of the bigger planetary body, that is the sun, and M actually stands for the mass of the Earth. So this is actually one kind of force that we would find occurring between the sun and the Earth, because we would find out the sun will try to pull the Earth inwards. Now there is also going to be another force that will act on this Earth. That is going to be the centripetal force. Now this one is a gravitational force as a result of the sun, and there is also another one that is a centripetal. I'm just going to write it as an F sub Cp, and that is given as v squared divided by r. Now in this case we have r to be the distance between the middle of the sun to the middle of the Earth. Now v is the velocity with which the Earth is moving. So I think I can well wipe this diagram out by now. Yeah. Now we already know that force is always going to be a force. Whichever kind of force we're using, there's still going to be forces. So since we know that the gravitational force, that will be F grav, since we know that that is equal to the centripetal force, then we can well say that Gm multiplied by small m divided by r squared, that is going to be equal to mv squared divided by r. Now from this place we know that r is going to cancel one of the r on the other side, and you're going to have the mass of the Earth cancel these other one. So this will leave us with v squared, and v squared is equal to g multiplied by m divided by r. So we need to hold this at the back, very useful. So I need to wipe some of this stuff out. Now we also know that as the Earth makes this orbit, we know this orbit is a circle. And you know that the perimeter around a circle is going to be the circumference. So let us say this is a cycle, and you have this Earth required to orbit this circle. There is going to be a time that will be taken by the Earth to complete this circle. Now, you could well express v, which is the velocity of the motion, in terms of that time. Since we have this to be a circle, we know that one circle is going to have 2 pi r, and that will be divided by the time taken to complete this distance. Now the distance around this circular orbit is given as 2 pi r, since we have the orbit to look like a circle. Now the time is going to be the period. That is the reason why you have a t right there. So you have this here. Now we already know that there is a v squared from the previous equation. So we're going to take this and plug it as v squared. So that will be 2 pi r divided by t, and this is squared. And this is going to be equal to g multiplied by m divided by r. So I'm going to wipe these out. Now we know this power over 2 will be distributed onto every term within the brackets. So that will give us a 4. And here we're going to have a pi squared, and we're going to have an r squared, and this will be divided by t squared. On this side, that is going to be equal to g multiplied by m, and that will be divided by r. Now remember, we need to find t squared. So we need to make t squared to be as a subject. First off, I'm going to cross multiply, and that will give me g multiplied by m multiplied by t squared. And on the other side, I'm going to have 4. That will be 4 pi squared r squared multiplied by the r. Now, I know that r squared multiplied by r, that is going to give us an r cube. And I need to make t squared as a subject. So t squared is going to be equal to 4 pi squared multiplied by r raised to the power of 3. And this will be divided by g multiplied by m. That is pretty much what they wanted us to derive. So this will be the answer. This is how to derive the period of rotation of the Earth around the Sun or any planetary body around another planetary body. In the case of the Moon around the Earth, that also works. So this is the answer to the first question. Now here is another question. Number 2 says, find the value of g, the universal gravitational constant, if the force of attraction is 2.07 multiplied by 10 to the second newtons. The mass of the planet is 5.98 multiplied by 10 raised to the power of 23 kilogram, and the mass of the Earth is 5.9 multiplied by 10 raised to the power 7. And the distance between them is 2.5 times 10 to the 4th meters. So we need to know that from the Newton's universal law of gravitation, we need to have the force of attraction between two bodies to be equal to g, the gravitational constant, multiplied by m, which will be the first mass. I might well write that as m1, and we're going to have m2. And this is all divided by r squared. Now r is actually the distance between the two bodies. Now in this case, we're required to find out what g is. So g is going to be equal to f multiplied by r squared, and this will be divided by m1 multiplied by m2. So we just got to plug all the parameters which we have there, and we'll just be right on our way. Now f is 2.07 multiplied by 10 raised to the power of 2. And you have the radius is squared. We have the radius. I should not actually call it the radius. It should be called the distance between the two bodies. So in this case, you have it as 2.5, and that will be multiplied by 10 to the 4th. So this is squared. Now this is to be divided by m1 multiplied by m2. Now m1 is the mass of the planet. So in this case, I'm going to write it. That is 5.98 multiplied by 10 to the 23rd. And that is multiplied by the mass of the Earth, which in this case we have it as 5.9 multiplied by 10 to the 7th kilogram. So let us find out what that's going to give. So you have that to be 2.07 multiplied by 10 raised to the power of 2. Raised to the 4th. This is divided by So that gives us 3.666883963 multiplied by 10 raised to the power of a 21. So I need to put that at the back. I'm just going to approximate it. So we should have 3.67. That will be multiplied by 10 raised to the power of a negative 21. So that is what you'll have. Now we know that the unit of the force is a Newton, and we have the unit of R squared, that is going to be meter squared, and this will be divided by kilogram squared. So that will be the answer to this question. Now you need to know that G, the gravitational constant, as the word indicates, this is actually going to be a constant. It turns out to be, in this case, that the value for the force that we were given is not actually the exact form of the force that might actually be present in that case. So depending on the force that you are actually given, you would calculate it and find out the original value, or the correct value for G should always be 6.67 multiplied by 10 raised to the power of a negative 11, and that will be Newton meters squared per kilogram squared. This is always got to be the value for the gravitational constant within the gravitational calculations. So just bear that at the back of your mind. In this case, we have that changing as a result of the fact that we had the force different from exactly what it should have been. So that is basically it. For the sake of the force that we were provided, this would actually be the answer to the value for the G, that is a universal gravitational constant. Now here is the third question. If a geostationary satellite is to orbit the Earth in 48 hours, then how high above the Earth's surface must it be located? Now the mass of the Earth is given in this case to be 6.0 times 10 to the 14th kilogram, and the radius of the Earth, that was given as 6.4 times 10 to the 4th. G, which is the gravitational constant, we have it to be 6.67 multiplied by 10 to the negative 11. Now we have already said that the period of rotation of a planetary body around another is actually given as t squared, and that will be equal to 4 pi squared multiplied by r to the third, and that is divided by G multiplied by n. So how can we use this formula in this equation, or rather in this question? So bringing out the parameters, we have that t, that is actually the time used for the orbit. That is the revolution, or should I say rotation, around the Earth. So you have this planetary stuff, which in this case is a satellite, and this is the Earth. So this stuff is gonna go around this Earth, and basically that will create an orbit. And the time that is required for that to happen is 48 hours. So in this case, we're going to say t is equal to 48 hours. Now we need to change this to seconds, because the period of rotation for a body is actually represented in seconds. So we just need to change that. Now we know that in 1 hour there is actually 60 minutes. And we also know that in 1 minute there is actually going to be 60 seconds. So that will be 48 multiplied by 60 multiplied by another 60. And this will now take us to the seconds. So we need to find out what that is going to give. So that gives us 172,800. That will be 172,800 seconds. So we need this. We're just going to place it somewhere. Next up, we need to find out what is the radius. Well, radius is actually exactly what we're looking for. So we might not well just go right on with it yet. I'm just going to leave it there and go to G. We already are given what G is. G is 6.67 multiplied by 10 raised to the power of negative 11. And we also have M. So M is a mass of the Earth as well as mass of the object. So what are we going to do? How can we actually solve this? Should we use the mass of the Earth, or should we use the mass of the satellite? Now, it's a very fortunate one here that we actually have the mass of the Earth only given to us. So stuff is actually going to come off easy now because you have everything given to you. So I need to wipe these out. So in order to find what the height is, we just need to find what r is going to be. So we need to make r the subject. I need to write t up here. So t is 172,800 seconds. So that should stay here. I'm going to wipe this away. So we need to make r to be the subject. Now r is actually the distance. Let us say this is the Earth and this is the satellite. So this satellite is going to take an orbit around the Earth. So in order to get r is actually going to be the distance between the middle of the Earth. I'm going to represent that. I think I need to use another stuff, so I'm going to use this. Let us say this is the middle of the Earth, and that must go to the middle of the Sun. Okay, so this is particularly what r is. Okay, and that obviously is going to be a kind of a height above the Earth where the satellite is going to be located. But we know that this is starting from the middle or the center of the Earth. So later on, we're going to use the radius of the Earth and subtract it from this r. That will give us a complete height. That is from the surface of the Earth. So in this case, I'm going to take these out. So we're going to go back. This is r to the third. This will be equal to, I just need to take it more gradually. So let us place this as r to the third. And we have 4 pi squared. And this will obviously be equal to g m multiplied by t squared. In order to find r cube is going to be g m t squared divided by 4 pi squared. So this might be some big one, so I need to be very careful with this. Now we got g. So what is g going to be? Now g is 6.67 multiplied by 10 raised to the 11th, negative 11. And this is multiplied by the mass. That is going to be the mass of the Earth. So that is 6.0 multiplied by 10 to the 14th. Then we have t. So t is actually this stuff. So we need to square it. That will be 172,800. We need to square that. And this will be divided by this stuff. That is 4 pi squared. So let us see what that is going to give. Okay, so that gives us 3.027. 3.027, and that is multiplied by 10 raised to the power of 13. So I'm just going to wipe these up. Yep. Now what is going to be the r? Obviously we need to take the power of 1 over 3 to both sides, and so that will take this out. And so r will be 3.027 multiplied by 10 to the 13, and this will be raised to the power of a third. So we need to find that. So that gives us 31,165. So that is going to be 31,165.0. I'm just going to leave it that way. So this is what we got. But I need to take this and express it in standard form. that would give us this is going to be 1, 2, and 3, and the 4. So we have it as 3.1165. That is multiplied by 10 to the 4th meters. So that will be the height from the middle or the center of the earth. So we're not particularly done for this question yet. We need to find what is the real height. Remember, we said that r is actually going to be the distance from the middle of the earth to the middle of the other planetary body. So we need to find what the height is. Now the height is going to be r multiplied by small r. Now this actually stands for the radius of the earth. We need to subtract this away from the bigger r, and that would give us the answer. So let us try to do that. So let us work that. Now we know that r is 3.1165, and this is multiplied by 10 to the 4th. And this will be minus r. R in this case is 6.4. That multiplied by 10 to the 4th. That is what we have there. So let us find out. So that gives us a 3.28. That will be a minus 3.28 approximately, and that is 10 to the 4th. So that is what we have for the height. Now, because we have that the height is never going to be a negative, you're just going to put this as a positive. So we're going to say that h is a positive equivalent of that answer. And so that will be a 3.28 multiplied by 10 raised to the 4th meters. So that is the answer to the question. The height above the ground where the geostationary satellite is to be will be 3.28 multiplied by 10 to the 4th meters. Now here is the 4th question. Derive an expression for the mass and the density of the Earth and calculate the density of the Earth. Now how can we solve this question? First off, we need to use Newton's law of universal gravitation as well as the formula for density of a material. Now we know that if you have the Earth, we're just going to call this the Earth. Maybe not so much of a perfect image, so maybe this is hopefully so good. And let us say you have an object on Earth here. We know that there is actually going to be a mass. I think I'm going to take these out and place it in this place. So let us say this is an object that was tossed into the atmosphere by some force F. So there is one force that will cause this object to return to the Earth. That force is called the gravitational force. I'm just going to write it as F grav. And in this case, the gravitational force acting on this object will actually serve as the weight of the object. And the weight of an object is written as the mass multiplied by the acceleration due to gravity. Next up, we know that generally the Newton's law of universal gravitation, that would always work on two bodies which are actually close to each other. And so we're actually going to have something like that. Now I'm just going to call it as a uni or universal law of gravitation. So we know that must be a g multiplied by m multiplied by small m, and that will be divided by r squared, where the r is actually the distance between the center of the Earth and the center of this body. So those are actually the two forces acting on these objects. Now, since we know that the gravitational force is the same thing as a universal law of gravitation, we're going to equate this two stuff. And that would actually help us to get the value of m. That is the capital M. because in this case we have the mass of the object as a small m, and that is also represented in the other. So since we have it that the gravitational force or the weight of the object is the same thing as a force due to the Newton's law, we're going to have that m multiplied by g, that will be equal to g multiplied by capital M, and that is multiplied by small m, and that will be divided by r squared. Now we want to find out what is going to be this mass, because that is what we are required to find out. We need to find out what is the mass of the earth, so we can use this method to do that. Now I need to cross multiply, so this is going to give us m multiplied by g multiplied by r squared, and this will be equal to g multiplied by uppercase M and smaller case. So in order to make this a subject, I just basically need to divide through by the coefficients of it. So that will be m multiplied by g multiplied by r squared, and that will be divided by g multiplied by small m. Now in this case, we can clearly see that m is going to cancel out, and we would have something like this. The mass of the earth is therefore going to be the acceleration due to gravity multiplied by the square of the distance from the center of the earth to that object on the earth's surface. So this is going to be divided by g. So that is what we have in the first case. Now we need to keep this at the back. We're going to use it in a little while. Now I just need to clear these out. Now next up, we know that the density of the earth, or density formula, is mass divided by volume. Now this mass is obviously the mass of the earth, so that will be used as this, and we need to find the volume. Now what is going to be the volume of the earth? Now the earth is majorly approximated as a sphere, so we know that the volume of a sphere, that is always 4/3 multiplied by pi r to the third. And here we have mass. Mass is equal to g r squared divided by g. This is the constant, and this is the acceleration due to gravity. So here now we actually have rho is equal to m. Now m in this case is going to be g r squared divided by g. And this is divided by v. V in this case, that is 4/3, and that will be multiplied by r to the third, right? So we need to rewrite this. That is going to be g r squared divided by g, and this will be multiplied. Well, I need to write it as a divided. So this is going to be 4r. Well, this should be 4r cubed divided by 3. So I could well change this, and this will be written as a gr squared divided by g. That will be multiplied by 3 divided by 4 pi r to the third. Now we know that r squared, he's going to cancel some stuff out. That will leave us with 1r below, and that is basically it. So rho in this case is equal to 3 multiplied by g, and that will be divided by the gravitational constant multiplied by 4. So I need to write the 4 in front of it. So this is 4 g, or let me place the pi before the g. So this is 4 pi g r. That will be the answer for the density of the earth. So we have the mass of the earth. Where is it? This stuff. We have the mass of the earth. That will be given as this, and the density, that is given as this. Now the next question is to find the density of the earth. So how can we do that? Now you already know that this is the formula to find the density of the earth. Now g stands for the acceleration due to gravity on earth. We know that is going to be 9.8 meter per second squared. We have g. This is the gravitational constant, and in this case that is going to be 6.67 multiplied by 10 raised to the power of negative 11 Newton meter squared per kilogram squared. Now we also have R. What is going to be R? R is the radius of the Earth. So that is going to be 6.4 multiplied by 10 raised to the power of 6 meter. Approximately, that is what you have. So we need to plug all these into perspective and find out what that's going to give. So we have a rho that is going to be 3 multiplied by g, and that is 9.8. We need to divide this stuff. So this is 4 multiplied by pi, and this is multiplied by g. We know g is 6.67 multiplied by 10 to the negative 11. And we have r. R in this case is going to be 6.4 multiplied by 10 raised to the power of the sixth. So let us find out what that will give. Okay. So that is 3 multiplied by 9.8. This is divided by 4 pi multiplied by 6.67 multiplied by 10 raised to the power of 11. That will be multiplied by 6.4 multiplied by 10 to the power of 6. So that gives you 5480 point, that is 0.6448 44826. That will be kilogram per meter cube. So that is the answer that you got for the density of the Earth. So here is the fifth question. Show that the work done to bring a unit mass from infinity to a given point is V is equal to negative gm divided by r. Now in this case we have g. That is equal to negative g. This is actually the gravitational constant, and that will be multiplied by m, which is the mass of the substance or the object in this case, and that is divided by r, distance from that point to the other point which you're actually trying to work. So we need to show that this is actually correct, or at least we need to derive it. So I'm just going to wipe it out. Now, first off, we know from the law of universal gravitation that F is going to be G multiplied by M1 multiplied by M2, and that will be divided by R squared. Now, let us say we had M2 to be the unit mass. Remember, we're actually dealing with unit mass. So let M2 be the unit mass, and that is going to be 1 kilogram basically. And so you are basically going to take that one and multiply it with this other stuff. And that will leave you with this. You're going to have a G multiplied by M1 and divided by 2. Now let us just leave this stuff as a G multiplied by M and divided by R squared. So this is what you have for the force of attraction from one point to another of the unit mass from infinity. As far as you have that mass as a unit mass, this is going to be the universal force equation. So we need to write it somewhere. Just going to place it here. This is divided by r squared. So let us write it there. So we need to find the work that is done in bringing a unit mass from infinity to another point. Now, we know that the change in work done, that is going to be F, that is the force, multiplied by the change in distance, or displacement in this case. This is what we know to be the formula for work done. Now, in this case, we can see that F is equal to this stuff. So we're going to take this and place it for F in this equation. So dW is going to be G multiplied by M, and that is divided by R squared multiplied by dr. Next up, we're going to integrate this stuff. Now, we would integrate it at upper and lower limits. So that will be integral dw. On this side, I'm going to write it as a w as the upper limit, and this is a 0. This is going to be the lower limit. This is where there is no work done at the time when we have not actually started working on the unit mass. And on this side, I'm going to have a r to be that point and infinity to be the starting point. So you got to take this stuff from infinity to a particular point. So that it will be basically it for the limits on the right hand side. Now we have a g multiplied by m divided by r squared multiplied by dr. Now we know that g as well as m in this case are going to serve as constants. So that is going to go out. So we should have an integral. W here is a 0. We have a dw, and we would have a g multiplied by m, and this is multiplied by integral at the upper limit of r, the position to which we want to take up this unit mass, and infinity. That is where we want to take the unit mass away from. And so this is going to be divided 1 divided by r squared multiplied by dr. That is basically what we're going to have. Now, if we wanted to integrate this side, that is obviously going to cancel. The integral of dw basically should give us a w. Now, that basically is going to be at the upper limit of a w and the lower limit of a 0. So on this side, I'm going to take it a little bit further. So this is the r, and this is infinity, and this is r raised to the power of a negative 2 dr. So I'm just going to wipe this stuff out. Now we know from here, from the law of the power rule of integration, they should give us, so I'm going to leave this w here, and you have this. And on this side, we're going to have a g multiplied by m, and we should have an r raised to the power of a negative 2 plus 1, and this will be divided by negative 2 plus 1. That is at the upper limit of, so that will be at the upper limit of an r and the lower limit of infinity. So that is what you got there. Now next up, we need to evaluate what the upper limit as well as the lower limits are. In this part, we need to take the upper limit and substitute the variable for it. So that is going to be a w, and that will be subtracted by the substitution with the lower limits. So that is going to be 0. If we substituted this as 0, that will give us a 0 in this position. Now we have g multiplied by m, and here now we're going to have stuff this way. We know that this should be r raised to the power of a negative 1, and this is also a negative 1. This is raised to the power of, well, not raised to, but the upper limit of r and the lower limit of infinity. So we really need to work the right hand side. On this left, we're just going to have a w, and so we have a g multiplied by an m, and we would have this stuff. Of course, this is going to be a 1 divided by r, and this is divided by negative 1 at the upper limit of r and the lower limit of infinity. So w is equal to g multiplied by m, and that is multiplied by this stuff. If we have a 1 divided by r divided by negative 1, that should give us a 1 divided by r. That is a negative 1 divided by r at upper limit of r and lower limits of infinity sign. Now next up, just as we did it on the left hand side in the previous case, we're going to take this and substitute it for r in the first case and subtract it with substitution of the lower limit. So this is going to be w. Need to rewrite it. So this is g multiplied by m, and here we're going to have a minus 1 over r. That is the first one. Now we need to subtract it with the substitution. That is the substitution of infinity should be subtracted from this. Now this whole stuff is going to remain, or at least the top part. And the lower part is going to be the infinity. That is we're substituting that variable as infinity. So that is going to be infinity, and that is what we're going to have right there. So w is going to be equal to g multiplied by m, And here we're going to have a negative 1 over r. And this is going to be plus 0. That is basically reasonable because we have that 1 divided by infinity. That should give you 0 because infinity is actually very large. So having 1 divided by infinity, that should give you 0. Now, negative 0 actually doesn't exist. Moreover, having a negative multiplied by another negative, that will give you positive. So we should basically have a negative 1 over r left. So in this case, we can see that W is equal to G multiplied by M, and that is multiplied by 1, or a negative 1 divided by R. And clearly we can see that stuff which is left for us is W, and that is equal to a negative G multiplied by M divided by R. And this is actually the same thing as we had in the initial case. We said that the work done in bringing a unit mass from infinity to a given point is given as this stuff. And here we can see this. So clearly we have proven it, and that is basically it. Now the sixth question says, a proposed communication satellite would revolve around the Earth in a circular orbit in the equatorial plane at the height of 3,500 kilometers above the Earth's surface. Find the period of the satellite in hours. Now feel free to pause the video and try solving it out by yourself. Now here we find out the only parameter which was given to us is actually only the height. And that is equal to 3,500. So you got 3,500 kilometers. Now, we need to find the period of the Earth. But before we go there, what is this height? What does it really mean? Now, from here, we said that the height of 35 kilometers is the height above the Earth's surface. So let us say this is the Earth. And you have a satellite. In this case, I'm going to represent this as a satellite. And this is actually required to orbit the Earth in this way. So we know that there could be a distance between the middle or the center of the Earth to the center of the satellite. That distance is called as the r. That is the distance away from the center of masses, of the two masses involved. But here we're not actually given the r. We were given the h. Now h, that is the distance away from the surface of the Earth to that position. This is h. So we need to get what r is. That is a smaller case r, which is actually going to be used to find what r is. That will be the radius of the Earth. So small r, that is the radius of the Earth, and I'm just going to write it that way. Now the radius of the Earth is 6,400 kilometers. But r is equal to the radius of the Earth added to the height above the ground required by the satellite. So let us find what r is going to be. Now we got to add 3,500 to 64. So this would give us 99. So we got 99 kilometer, and we could well change this to meters. So r is equal to 9900 multiplied by 1000, and that is a meter. So r obviously is going to be 9 million, and then you have this. So we need to express this in standard form. So this is going to be 1, 2, 3, 4, 5, and 6. So this should be a 9.9 multiplied by 10 to the 6th meter. So we really need that. I'm going to place it somewhere here. R is equal to 9.9 multiplied by 10 to the 6th meter. Yep. So the next step, we need to bring out the Kepler's law equation. We know that is t squared, and t squared will be equal to 4 pi squared multiplied by r to the third, and that is divided by g multiplied by m. Now we know that G is a universal gravitational constant. So that is 6.67 multiplied by 10 to the negative 11 Newton meter squared per kilogram squared. Now we also need to find M. Now M is the mass of the Earth. So the mass of the Earth, that is 5.98 multiplied by 10 raised to the power of 24 kilogram. So from here we can pretty much find out what T is. Now you need to know that newtons, that is going to have its values in seconds. So this period, that will be found in seconds. Well, we are required to find it in hours. So first off, we're going to find the period in second and change it from seconds to hours. So t squared, that is equal to 4 pi squared multiplied by r to the third. Now r is 9.9 multiplied by 10 to the sixth. And that is to the power 3. Now we got to differentiate. Whoa, that is divide. So this is 6.67 multiplied by 10 to the negative 11. And we're going to multiply by 5 multiplied by 9.8. And this is 10 to the 24. So that is what you have there. Let's see what that's going to give. So there we have 4. And 4 is multiplied by pi squared. So this is squared. And this is multiplied by this raised to the power of 3. So we know that is 9.9 multiplied by 10 to the sixth. We got this divided by 6.67 multiplied by 10 to the negative 11. And then that should be 5.98 multiplied by 10 to the 24. Okay, so I need to raise that to the power of 24. So that gives us 96. Well, the number is pretty long. I'm just going to hold this close to me. This is T2. T2 is 96. We got 0, 36. We got 937.53. Now this is obviously in seconds, so I'm just going to write that there. Need to write it out. Well, I'm just going to leave it. So we need to find out what T is going to be. So T is going to be the square root of the answer there. So that will be the square root. So that is a 960.36937.5. Okay. So this gives us 9799.84 approximately. And this obviously is in seconds. So we need to change this from seconds into hours. Now, how many minutes or how many seconds are required to make a minute? That is going to be 60 seconds. So if you divided this by 60, that is going to take you to the answer in minutes. Now, in 1 hour, we also need 60 minutes. So I'm going to change this. So that is what you're going to have. So we need to divide that by 3600. So this is divided by 3600. So we're going to have 2.72. So that is what you have. 2.72 hours. That will be the answer to the question. So now this is the 7th question. It says, calculate the weight of an object on the moon if it weighed 36 newtons on Earth. Now also, if a person can jump 3 meters on Earth, how far can he apparently jump on the moon? So we actually have 2 questions here to solve. Now, we have the first parameter given to us. That is actually the weight of an object on the moon. So that is going to be written here. I will just write it as the weight on the moon. And this is 36 newtons. Then we need to find what the weight of, well, this is actually the weight on the Earth. So I'm going to take this out. and I will write the other one. This is the weight on the earth, and that is 36 newtons. So the formula of the weight of an object on the moon with relationship to its weight on earth is actually written this way. You have the weight on the moon divided by the acceleration due to gravity on the moon, and that is equal to the weight of the object on earth divided by the acceleration due to gravity on earth. So what is g of earth? That is the acceleration due to gravity on earth. That is obviously 9.8 meter per second squared. Now the acceleration due to gravity on the moon is actually 1.63 meter per second squared. Then we also have the weight of the object on earth. So that will be WE. That is written as 36 newtons. So we need to find WM. Right? Now from here, we have that WM is going to be equal to WE multiplied by G of the moon, and this divided by G on the earth. So that is what we're going to have. So W is going to be equal to, I think this is W on the moon. That will be equal to W of the earth, which is actually 36. And this will be multiplied by G on the moon. So G on the moon is 1.63. And this, of course, is divided by G on the earth. So that will be 9. That is 9.8. So let us find out what that is going to give. So that gives us 5.9877. So that will be 5.81. That should be 5.9877. So I might just write it as 98 like that. And so that is what you have. That will be the weight of that object on the moon if it weighs this on Earth. And this is actually reasonable because the weight of an object on Earth must actually be higher than the weight of the same object if it goes to the moon. Now the next question there is for us to find the height which a person can actually jump on the Earth, well rather on the moon, if he's able to jump 3 meters on the Earth. So what formula can we use to solve this question? How are we going to solve it? Now, the height that the person is able to jump on the moon, we're going to represent that as h sub m. And the height the person should be able to jump on Earth, that should be h sub e. This must be equal to the square root of the acceleration due to gravity on the moon divided by the acceleration due to gravity on the Earth. So we need to find what the height will be on the moon. That is h sub m. Now h sub m should be equal to h sub e multiplied by square root of g on the moon divided by g on the Earth. Now h on the moon, well h on the Earth rather, that is the height the person jumps on Earth. That is 3 meters. So we need to multiply that by the square root of the g on the moon. Now g on the moon is 1.63. And this is divided by g on the Earth, which is 9.8. So that gives us 1.22. So this is going to be equal to 1.22 meters. So h sub m, that is equal to 1.22 meters.